Greetings of the day. In this lesson, we will learn the two important graph traversal techniques. In the previous lessons, we have understood what a graph data structure is, the different terminologies associated with the graph data structure, the different representation, and the advantages of each type of representation of a graph data structure. In this lesson, we will understand the two types of graph traversals. The first one is depth first search algorithm, wherein the technique recursively explores as deeply as possible before backtracking. The C implementation of depth first search algorithm includes recursion and a stack. The algorithm starts as follows. The second technique is the breadth first search algorithm, which visits the neighbor at the current depth before moving to the next level. The implementation uses a queue. So, this is the first difference between the depth first and the breadth first search algorithm. The depth first search algorithm works in the following manner. It starts by putting any one of the graph's vertex on the top of the stack. Take the top of the item of the stack and add it to the visited list. Create a list that vertex adjacent nodes. Add ones which aren't in the visited list to the top of the stack. Keep repeating the steps 2 and 3 until the stack is empty. So now we shall move to the algorithm by taking an example. Here is a undirected graph with 5 vertices. So we have two important points to understand here, the visited and the stack contents. We start from vertex 0. We start from vertex 0. The DFS algorithm always starts by putting it in the visited list. So 0 is put on the visited list and all the adjacent vertices on the stack. The adjacent vertices to node 0 or vertex 0 is 1, 2, and 3. Sorry, let me correct this. The adjacent vertex to the node 0 are 1, 2, and 3, which are put on the stack. Next, we visit the element on the top of the stack. So the top of the stack is now 1. So we visit that node and mark it as visited. Next, visit the element on the top of the stack, that is 1, and go to all the adjacent nodes. The adjacent node of 1 is 0, which is already visited. So we visit 2 instead. And next, we mark 2 as visited and put the nodes that are connected to 2 on the stack. So the nodes that is connected to 2 is 4 and that is put onto the stack. The vertex 2 has unvisited adjacent vertex that is 4. So we have put it on the stack. Next we visit the next element on the top of the stack that is 4. So it doesn't has vertex 2 has an unvisited adjacent vertex 4. So we add that onto the top of the stack. Vertex 2 has an unvisited adjacent 4. So we add that to the top of the stack. Next, we visit the last element that is 3. It doesn't has any unvisited elements. So we put it to the visited list. So now this completes the traversal process. So summarizing, the step involves visiting the nodes and putting all the connected nodes onto the stack and retrieving one by one. So now let us look at one more example to understand the process. So depth first search algorithm utilizes the stack to perform its task. So first, the node S is put onto the stack. Next, and it is marked as visited. Next, all the nodes that are connected to S, that is A and B, is put onto the stack. We select the element on the top of the stack, that is A, and put the other elements that are connected to A that are unvisited onto the stack, which is D. Next, we visit the element on the top of the stack, that is B, and put the node that is connected to D on the top, that is B. Next, we visit the node on the top of the stack, that is B, and it has only one connected node, that is yes, which is already visited. So next we pop out D and we will put all the nodes that are connected to D on the stack. So finally we have C, D, A and S. So this is the process of depth first search traversal in case of graphs. So now we shall look at the code to implement this methodology. So let's go to the compiler and start building the code from scratch. So now we are learning the C code implementation of depth first search algorithm. So let me start from here. Every vertex has a label and a bool variable called as visited to indicate whether it has been visited or not. And we also have, so we will start building the code now. The first thing is we have a node which consists of a vertex and a pointer to the node. So this is the first declaration. The second declaration that we have, so this is next, sorry. So we have a function. Let me show you a simpler version. Yes, let's understand this. So we first create a structure of two variables, that is the char label and bool visited. So we have a label assigned to every vertex. Next, we need to declare a stack, which is the array implementation. And initially, the stack is empty. So when the top of the stack is -1, it indicates that the stack is empty. So this becomes the global variables. So next we are going to create an array of vertices. Because we have multiple vertices in our program, the maximum vertex that this program can take is 5. So you can make as many maximum, we can make the program to accommodate as many vertices you want by changing this. So this max variable indicates the maximum number of vertices vertices in the graph. So we are creating array of vertices. Then we need an adjacency matrix. So whose order is max max. So if I have a graph of 5 cross 5, the order of the matrix is 5 cross 5. So initially we can keep the vertex count as 0. So next we have already discussed in our stack program the 5 important operations of the stack, which is push, pop, peek, and is empty. So we know that push involves putting an element onto the stack and pop involves returning the element, and each time the top pointer is updated. Peek is just to know the value on the top, and stack empty function returns a bool value to tell me if my stack is empty. Next, we have already discussed this logic in our tree chapter to add a vertex. So we will have a label. So the vertex is created using the dynamic memory allocation function, which is malloc. The label value is assigned to the label that we for, and visited value will become false initially. And we are updating the list. So we have created an array of vertices. So we are updating the count. And we are appending the newly created vertex to the array of vertices. So next task is to add the edge to the edge array. Edge indicates that the two vertices are connected. That is, let's assume I have 2 is connected to 3. So it means that I need two entries in the adjacent graph to be equal to 1. That is, mat of 2 of 3 and 3 of 2, both the elements should be assigned equal to 1. So the next task is to display the vertex. So that is nothing but which is the array element, label member of the array element. How do we get the adjacent unvisited node? So we will look for the condition where the adjacency value is equal to 1 and also if the visited value is false. So this is the most important segment. So the condition, both the conditions are to be satisfied in order to get the adjacent unvisited vertex. Next comes our depth first search algorithm. So we will mark the vertex as true and we will display the vertex. So we will push the vertex index on the stack. If the stack is empty, we need to get the, until the stack is empty, we need to get the next unvisited node. If no adjacent vertex is found, as per the algorithm, we pop. Else, we make the unvisited node to be equal to true. We will display the vertex and then we will push the unvisited vertex of that particular node. If the stack is empty, it indicates that the search is complete and reset the visited flag. Using the for loop, that is, we have array of vertices, all the visited flags will be set to false. So now in the beginning, we are setting the adjacency matrix to 0 and finally we are creating a graph here. So this is the graph that is created. So these are the labels and these are the edges. So we call the function that is the depth first search algorithm to give us the traversal. So summarizing the steps. So we have the vertex defined as label and visited. We have the stack variables and the array of vertices that we have created because we need to store the label and the condition of visited to be either true or false. Then we have different stack functions, pushing, popping. Then we have the logic to add a vertex, add a edge, display the vertex. We have an exclusive function to get the adjacent unvisited vertex. Then the algorithm of depth first search is employed until the stack is empty. Once the stack is empty, it indicates that the search is complete. In the main driver course, we define the vertex and the edge and call the depth first search algorithm. So this completes the discussion on depth first traversal algorithm. Next, let's move on to breadth first search algorithm. This algorithm utilizes the queue instead of a stack. We start by putting one of the graph's vertex on the back of the queue. Take the front item from the queue and add it to the visited list. Create a list of vertices adjacent nodes. Add the ones which aren't visited in the list to the back of the queue. So we keep repeating this step until the queue is empty. Now let's understand this with the help of a program. So here is a graph with 5 vertices. So we have visited and then we have the queue. We visit the start vertex and add all the adjacent vertices to the queue. So which are the adjacent vertices to 0 is 1, 2, 3 and this is put on to the queue. Next, we remove the element from the queue which is 1 and mark it as visited. So we mark this as visited. So visit the neighbor of start of 0 which is 1. So the next step is we dequeue the element which is 2 and mark it as visited and put the node that is connected to 2 onto the queue as we can see here. Next, we remove the element on the front of the queue and mark it as visited so that the queue element moves forward. Next, we dequeue the element from the queue and mark it as visited. So these are the steps that are involved in breadth first search algorithm. So this employs a queue data structure instead of a stack data structure. So now let us see the code for the breadth first search algorithm. So very similar to the previous implementation, we have we have the vertex, and instead of the stack variables, we have the queue variables. Similar to the depth first search algorithm, we have the list of vertices, the adjacent matrix, and the list of queue functions, that is enqueuing and dequeuing and QMT. We have a function to add the vertex to the vertex list and to add an edge to the edge array. So the logic to get the unvisited list is very similar. That is, the condition is that the entry of the adjacent matrix should be equal to 1, indicating that there is a link, and the label, that is visited label, the bool value should be equal to false. The breadth first search algorithm is implemented, that is the process of putting the element on the queue and removing the data from the queue in the method that we have discussed until the queue is empty. So once the queue is empty, we just stop the search process. The first process is removing the data. So if the queue is empty, it will stop, otherwise we have a data, and we will make that point as true, and we will display that vertex, and we will insert the unvisited vertex onto the stack. So once the queue is empty, we will reset the flags. So similar to the previous program, we have defined the graph by adding the vertex and the edge. And finally, we will print the traversal path. So this is the breadth first search traversal for the graph that we have defined. The practical consideration for the graph data structure is that it can consume significant memory. So there are the different representations and algorithms that work on graph. So choosing the right representation is very important. The selection depends on the applications and the operations that are performed on the graph. So with this, we conclude a session on graph traversal.